Hello everyone, I'm Nastaran Saffaryazdi. I'm a PhD student at the Empathic Computing Lab at the University of Auckland. Today I'm presenting our research on emotion recognition in conversations using brain and physiological signals. Nowadays, recognizing emotions is essential in many human-human and human-computer interactions. The effectiveness of our remote interactions, therapy, consultations, or training sessions could be improved if they were equipped with emotion recognition systems. Also, creating intelligent agents with emotion recognition capabilities could be useful in healthcare, education, entertainment, and safety. This essential need motivated us to conduct our research on exploring emotion recognition strategies during our interactions. When an emotional stimulus happens, our brain sends signals to different body organs to regulate the body condition, and many physiological and behavioral changes happen in our body. Emotion recognition methods use one or a combination of these cues to recognize emotions. Researchers have modeled emotions in two main categories to measure emotions, including the discrete emotion model or Ekman basic emotions and continuous or dimensional emotion model, including arousal valence and arousal valence dominance dimensions. In our research, we used two-dimensional arousal valence model and basic emotion model for measuring emotions. Many studies use behavioral cues such as facial expressions, audio, and text for emotion recognition, and several datasets have been created using behavioral modalities. However, behavioral cues may not reveal the underlying emotions in our daily interactions because people can control or fake their behavior. Some other studies focused on using brain and physiological signals to overcome behavioral weaknesses. Most research used passive tasks like watching video clips and images or listening to music to induce emotions. However, our daily interactions include active tasks such as talking and movement, which directly affect the brain and physiological signals. Also, many studies have been done on emotion recognition. Only a limited number of them have focused on exploring physiological signals in non-passive tasks, and none of them have used brain and physiological signals to recognize spontaneous emotions in non-acted face-to-face conversation. To address this gap, we came to two main research questions, which are: can we create a conversational setting where people could feel emotions spontaneously and build a multimodal dataset in this condition, and can we use the human brain and physiological responses to recognize emotion in this condition? To answer these questions, at first we conducted a user study and recorded brain and physiological activities during face-to-face conversations. We recruited 23 participants from university staff and students, including 13 females and 10 males, aged between 21 to 44 years old. In this study, each participant had a conversation with a confederate person about their emotional experiences, memories, or their imagination of emotional scenes. The confederate person was a peer-intern psychologist trained in consulting and therapy conversations. We used OpenBCI EEG cap to record EEG signals and Schirmer sensor to record PPG and GSR signals. We also recorded audio and video for further analysis. Each participant had a conversation for about 10 minutes for each of sadness, anger, neutral, fear, and happiness emotions, subsequently in random order. We used a self-report questionnaire for ground truth labeling. After the experiment, we asked participants to listen to some parts of their conversations and report their emotional state for the beginning, middle, and end of their conversations based on basic emotions, arousal, and valence levels. To evaluate the effectiveness of conversations in inducing emotions, we compared the self-report ratings with the target emotions You can see most participants, especially for happiness and sadness, reported the target emotions. Also, we evaluated the content of conversations using LIWC 2015 software, which counts words in psychologically meaningful categories. LIWC statistics showed that the number of used words was related to the target emotions for most participants. The results indicate that our experimental setting was quite effective in eliciting spontaneous emotions. To recognize emotion, we applied similar processing steps to EEG, PPG, and GSR signals. We first applied several pre-processing steps like data cleaning and splitting trials in 2-3 equal parts similar to data labeling. Then we divided data into the training and test sets. Then we extracted time series of features from each signal using a 5-second moving window with a 1-second step, and then extracting features of each window. We extracted EEG band power, some statistics of GSR signal, and heart rate variability features and PPG statistics to make the feature vectors. The time series of features have been fed into a stacked LSTM to extract temporal features. Then we used a dense layer with Adam Optimizer to classify each signal based on arousal valence or emotion labels. Finally, we used a weighted decision fusion method to fuse all these modalities. Our result shows that our model achieved satisfactory results in terms of F-score in both subject-dependent and subject-independent approaches. The F-score of the subject-dependent approach is considerably higher than the subject-independent approach because physiological responses are different in various people. Also, people's personalities affect their emotional responses. Because of these differences, it is challenging to design general models for recognizing emotions. We also compared the result of LSTM with random forest classifier or RFC when applied on feature vectors. The performance of the LSTM method is considerably better than RFC in most cases. Also, the fusion strategy classified arousal labels effectively in the subject-independent approach and emotion labels in the subject-dependent approach, but it couldn't improve the result in all cases. To conclude, we could create an effective conversational setting for inducing spontaneous emotions. We also created a multimodal dataset of the brain and physiological signals in conversation, which is helpful in training robust models for recognizing emotion. Finally, we evaluated our strategy in recognizing emotions using both subject-dependent and subject-independent approaches and achieved satisfactory results. In this research, we faced some limitations that need further investigation. Some sensor limitations like setup difficulty, variety in mood and personality, ground truth labeling for smaller chunks of data, and mismatching between modality predictions should be more explored in the future. Also, using other behavioral and physiological modalities and exploiting robust deep learning methods and effective fusion strategies could improve the recognition result in the future. Thank you for your attention, and now I would be happy to answer any questions.